Hello everyone and welcome to another roundtable with Matthew and Russell. We're going to be now talking about Cerberus and atomic composability, something that I think is super cool, but a little deep. So let's...
Very deep.
Yeah, very deep. Let's start with what are the key features of Cerberus and what is Cerberus?
Yes, let's define Cerberus,
Yes.
since not everyone has watched 200 Radix videos.
Of us going, Cerberus!
Cerberus, right. So Cerberus is the consensus algorithm that powers all of Radix. This is for any decentralized network. This is basically the decision, the algorithm that powers what are the things that we all agree to mark as the correct history.
Right.
And of course, the definition is 9 pages longer than
Right.
that, but that's what it's all about.
Right.
Coming to an agreement on, yes, this thing happened, this other thing we rejected. So Cerberus, the key features, and it's a novel consensus algorithm that is unlike anything else that is out there. Number one is linear scalability. This is the ability to be like the internet, where if I need more throughput, I add more servers.
Right.
This is quite hard to achieve, and we're very excited that we've cracked it. The second one is fast finality. And finality is how long, like when can I say that a transaction is settled?
Right.
It's not going to change and I can now act on that.
Right.
And this is something that there's a couple of different models, and we can talk about that a little more. But for now, it's important for us to know that we do want settled finality in a short time. That's a feature of Cerberus. And then the third one is atomic composability, which is another one that you can explain for days, but basically it's everything can see everything in one transaction. So any asset, any application, they can all see each other. They all act on the same up to the moment information, right. And they process that as a single unit, or if the transaction fails, the entire thing fails and nothing changes.
And the unique thing about Cerberus there is that it doesn't care about sharding. You can shard the network as much as you like,
yes,
but you can still make sure that every consensus operation can essentially draw any application, any asset together across that massively sharded infrastructure.
And this was to achieve that linear scalability.
Yeah.
Without sacrificing composability.
Yeah.
I mean, that's our secret sauce, right?
Right.
That was the beginning of the, we finally cracked it.
Right. That was like 7 years.
That was a long time.
7 of the 9 years was that. And so what makes Cerberus different for me? Like, one of the things that I think is interesting that people talk about a lot is this idea of parallel execution. I wonder if you could give a bit more clarity on like how Cerberus works on this idea of parallel execution as well.
Yeah, because when you're generally talking specifically on the throughput part of it, finality is a bit of a different question, because you can, you could have something that processes lots of transactions, and finality is like, well, do I have to wait an hour for my transaction? Right. But setting that aside, if you're focused purely on how many transactions can you get through this network, there's sort of one of two ways you can go, just theoretically speaking. You can either process all transactions in a single order and do it as quickly as possible, or you can say, we're going to allow multiple things to be processed in parallel.
Right.
And generally, the serial approach is kind of where you start. This is sort of like the easiest to understand thing. It's like, all right, we're doing things in order. Right. Let's try to do them even faster. Right. And let's see how fast we can make it. Right. So it's sort of the direct approach to the whole thing.
That's
Parallelism.
That's the Bitcoin model. That's the Ethereum model. That's essentially what blockchain architecture was designed around.
Right, and in fact, I mean, there's even sort of historical precedent for this. This is even how computing in general used to be. It was everything was like faster processors, more clock speed.
Right.
And then, much like computing, at some point they realized, there's a limit to what you can do with that.
Right.
In some sense, at some point, you're going to be doing many things on this computer, or for distributed ledgers, we're going to be processing many transactions on the ledger that have nothing to do with each other.
Right.
So if we can start with that assumption, which is a very good assumption, particularly if you're talking about global scale DeFi,
right.
Me buying a coffee has nothing to do with a million other transactions happening across the world. Right. So it's a good assumption to make. And if you do that, parallel processing has a lot more headroom. If you can do that well, the sky's the limit in what you can achieve. So this was our focus from the beginning. It's like, well, parallelism has to be the way forward on this stuff. Even if it's the harder problem to solve, which it generally is. It's, again, the computing paradigm here is, building a parallel processor and building an operating system that knows how to do parallelization. required some additional work. It wasn't the obvious approach, but this has been the guide star for the 10 years is like, this is the problem we must solve, or else we don't actually have a solution.
Right. And so let's break those down a little bit, what you said, Russell. So linear scaling, fast finality, atomic composability. Can you sort of talk a little bit about how linear scaling is achieved and why it's important?
Sure, and so linear scalability, the way we do this is to achieve this parallelization that he's describing, we pre-shard the entire space to say there's this enormous number of shards that you can ever possibly use.
Right.
And we basically, anything on the network is associated with a certain shard in this massive, massive space.
Right.
And then we have these sets of validators, which are able to serve some segment of that shard space based on their capacity and so forth. And the way this works is you can think of it is, as you add more and more validators to the system, I now can have each set of validators paying attention to a smaller set of shards. And because of that, I can dramatically increase my overall throughput. Now, of course, getting into, I'll cheat a bit into atomic composability on this, is that, but what if I'm being served by this validator set that has this information, but I did talk something on the other one? Being able to synchronize validator sets for a transaction, do the work together, agree on state, and then separate again so you can again process unrelated things. That was the really tricky bit.
Yeah, and that's sort of the essential bit, right? Because in DeFi, as you say, you can assume complete parallelism, right? You can just say something is embarrassingly parallel. It doesn't care what is happening at any given time because it's just assuming everything isn't related. Now, for a lot of transactions, that's true. If you're thinking about the world transacting on a shared piece of infrastructure, your assumption being that all of these transactions are unrelated, or the assumption being all of them are unrelated is narrowly incorrect, but majority correct. Right? However, you do have the problem that there are things that are related. If we think about a DEX, a decentralized exchange, and we have multiple transactions trying to hit the same pool where they're trying to buy something and sell something, the ordering really matters, because you now have this idea that each time someone buys, let's say they're all buying in the same direction, you are going to have slippage. And so whether or not you're first in the queue or last in the queue, that makes a big difference to what price you're getting. So you have this problem, you have this dual problem. Parallelism is the right way to go, but you also need to have a way of going, what things are related so that we can make sure that they are processed in the right order. And on top of that, if you want atomic composability, where I want to go, let's say I've got a lending platform and I want to borrow a flash loan from a lending platform, trade on a DEX, and then return the results to that back to the lending platform. I'm now pulling together two potentially contentious operations that have to be ordered. So like, how do we do that? How do we solve that problem in Radix?
I mean, this gets into the whole stack.
It's a full stack solution is the answer.
Yeah.
That's right. There's on this one, there's an entire white paper to go read on this very topic. I think we'll be doing this for 10 more minutes if we get into how do we know what state is related. A lot of this is related to the Radix engine.
And the transaction
manifest. You think of it as like, what's the minimum ordering we can get away with in all cases, right? That's what we've achieved with this.
Yeah, and you need to, I mean, it really does propagate to all parts of the system, because as you said, it's a really interesting point, because parallelism is the general case, most things, but when things are related, it's very, very important that they're related. And you need to have no limitations to your ability to make those things related. Like, I need to be able to say, even though these two things on other sides of the network haven't ever talked to each other before, for this transaction, it's really important that I can talk to that thing, which means that you have to kind of commit to the approach. It means that you have to, I think a lot of the scalability approaches that kind of play with sharding don't really commit to it. They sort of say, well, we're going to do a little bit of sharding, but within each shard, then we're going to process things serially, kind of, minimize the disturbance. But, but then the problem here is you haven't really gotten nearly enough parallelism, but you've also then broken your ability of operating across those shards. So you kind of get the worst of both worlds. You don't get enough scale for it to matter, but then you've broken the thing that you really need. So this is the investment we made in the whole thing, and it really did bubble all the way up the stack. It was not just the consensus algorithm. It was the fact that we had to build a virtual machine layer for smart contracts that was able to specify those dependencies to say, for this transaction and only this transaction, this smart contract and these 3 accounts are interacting together. Consensus, go figure that out. And then that had to go up to the transaction level as well, because we needed to be able to, when you're submitting a transaction, to tell the Radix engine, hey, this is what I'm trying to accomplish. Please translate that into the set of shards that need to be handled. I don't have to deal with shards at the smart contract layer. I don't have to deal with shards at the transaction layer. I just want to tell the network. Nor at the crypto layer,
Where my stuff's running.
Exactly. It's like, I just want it, from my point of view, I just want to be able to do anything I want, whenever I want, with whoever I want. And the system needs to be designed to translate that into shards that it can pull together.
Yeah, which is what I think is so brilliant from a developer point of view in Radix. Anyone who's spent time building on any sharded infrastructure on other ledgers knows how much the developer has to care about how they're dealing with sharding. On Radix, it's basically just abstracted away. It's something that, because you can call anything, you don't have to think about what shard am I on, what shard am I calling, which I think is the only real way forward, to have those levels of indirection that deal with it at the low level.
No one wants to have, you know, a set of 24 internets, and you have to decide which internet do you want to deploy on.
Where are all my friends? What are the apps I want to use? What if I guess wrong? What if everybody just crowds on to internet 12 because that's where all DeFi is happening? Now we've solved nothing because we effectively have DeFi running on a single shard.
Which, you know, just like, and as you say, this is a really deep topic. There's lots of stuff in there. I think the transaction manifest is my favorite example of how that goes all the way down to the full stack, because not only does it help a user understand what they're signing, goes all the way down to helping consensus understand what's related and what's not, which I think is just like,
everybody wins.
I love it. It's so good.
It's all synergistic.
And it's logical. I think we've mentioned this before, that in some ways the transaction manifest, I guess we'll talk more about this later, but we sort of it was like discovering this laws of physics, like you were saying. It's like we realized, wait a minute, this makes sense. A transaction should be about the intent of my transaction. And with that, you can translate that all the way down, and you can translate up to the user. It's just the right solution.
You also talked about finality.
Oh yes, finality. I don't want to give it short shrift.
Why
let finality have a word
matter?
here. So you can think of it as, it's really important, especially in finance, to know, okay, that's settled, I can now act on that. And you have things like Bitcoin, where you have probabilistic finality, where it might be that for me, I say, well, after so many blocks, I think that's final, I'll act on it. You might disagree with what that number is. And so in any place where you have probabilistic finality, it's not one.
It's not one.
To go back to your DEX example, that can't work with probabilistic finality because of, each trade impacts the price of the next trade. And so if suddenly something 12 trades ago vanishes, that's a big problem, because now everything's been acting on incorrect. God knows what happens with the numbers, So this is it was
become complicated.
It would be a really difficult thing to unwind, So it's really important that we do have that notion of finality, that hey, this is settled, you can move on to the next thing.
Yeah, and I think this also gets into user experience as well. It's another one of these things where, if I'm paying for something or doing something like this, I want to know, I submit it, I wait a very short amount of time. It's like I run my credit card, all the things that we're used to for the world. It's like there's a very small amount of time in which the thing I don't understand works on it and comes back and goes, that was good, or that was not good. If you can't provide that, then no one's going to want to do this. And no one's going to say like, well, okay, well, you've now got 48 confirmations. It's up to you to decide whether or not that's final enough for you. Like,
so what is finality on Radix?
It's deterministic finalities, which means that they're kind of these two classes of consensus algorithm. One of them is the probabilistic one that Russ mentioned. The other is sort of BFT style, which basically means there is a known threshold where once a sufficient weight of the network has voted in support of something and says, yes, this is in fact a valid transaction, you can deterministic basically means that there's a known rule set. You can say for certain that the math has been satisfied and you may now consider this final. And the rules of the network say you cannot roll back at that point. This gets into whether or not you guarantee safety and liveness, and it gets into these very sort of deep consensus topics. And it's interesting because the traditional consensus design world started with BFT. This was the thing that went back to like the 70s and earlier, was everything was BFT. Before consensus networks, before decentralized networks were a thing, it was just a distributed computing thing. And then we kind of took a left turn on it because Satoshi Nakamoto showed up and basically invented probabilistic consensus.
Right.
Which was great for liveness, right? That was
right. It was amazing. It was
beautiful.
like you could have this network where anybody could join this thing and the network will just keep going.
Right.
And it did it through this sort of economic means. It was a brilliant thing. And it threw the academic community that had been looking at BFT stuff into a frenzy, because it was like this, it was they weren't even trying to solve the same problem. But what we realized a few years later is that some of those researchers started applying some of the lessons from that and goes, oh, actually there are economic mechanisms in these systems are really powerful. We never thought of that before, because if you're just talking about a shared sort of set of computers that I own, there is no economics involved. And so, we got through many of, I guess basically since Bitcoin came out, there was Tendermint, and then there were a few generations of these BFT algorithms. And we very much leveraged a lot of that work through Tendermint and Cosmos and Hot Stuff and a lot of these BFT algorithms. We used that and then added on the sharding coordination component of it, basically.
I mean, the main thing that we did that I think is sort of like important to draw out of that is this idea of, if you are going to shard, then shard in a deterministic way and shard massively.
Right.
And so just start off by going, it's going to be sharded.
Yes.
You're not going to be able to store everything. So instead of trying to like nibble at it, but keep things as a one shard algorithm, instead go, okay, it's going to be a massive shard space, in our case 2 to the power 256 shards, which is something like close to the number of atoms in the universe or something like that. I can't actually remember what the magnitude is, but it's around that.
Right.
It's more than we'll need.
It's more than we'll need. It's more that you can store the entire contents of the internet and still only have like 5 bytes per shard or something like that. And then but then you go, okay, well, the consensus algorithm is a cross-shard algorithm. It is designed to go across shards and coordinate between them.
And you're going to need rules to decide what shard does this go. It's not a matter of, at this point, you're not even thinking about the question of, well, which shard does the developer choose to deploy to? It's like, no. It will be automatically sharded.
Right.
And you just have to come up with the rules of how you assign shards. So it's a different design philosophy from the start.
Right. But what is the speed of finality on Radix? What can I expect? We said fast, but what does that mean?
I mean, as when we get to the fully sharded world of Xi'an, we're aiming at something like 5 seconds. Right now, I believe we're at sub-second or so on Olympia, but we're on a single shard, right?
Yeah. Right. I mean, the great thing is it's basically just limited by the speed at which enough nodes to come to agreement can communicate with each other over the internet. It's mostly limited just by internet latency and this sort of thing, which, as it turns out, getting a reasonable number of nodes to talk to each other and vote on something happens in less than a few seconds, which is less than what you expect from running a credit card.
Right. So sort of 5 seconds is what we say, but right now we're well better than that. But all of these are fine for a point of sale activity. Nobody will mind waiting through Radix Finality. Okay, and so you mentioned Xi'an, right? Mm-hmm. So what is Xi'an and what have we got today? So what is Olympia? What's Babylon? Is Babylon fully sharded? Babylon is not fully sharded. Right. Babylon is still, we have a single shard running. Yep. And so let's start with what's Olympia, since we're coming at it from there. Yeah. Olympia was, let's get consensus running. Let's stand up our first 100 validator set. Right. Let's prove out the concept that we have these powerful native assets. We have an early version of the Radix engine on there. And basically, let's make sure that we can get things like 100% uptime, and we can understand how to change the network protocol safely and all that. And that's all been going terrific. And so Babylon is, okay, now the fun stuff begins, which is let's put programmability on the network, which also, when you have that, we get this brand new user experience and we get this whole new transaction model. And Babylon is like the kind of the moment I think everyone's waiting for. Of cool, you guys have proved you're credible. You can, you deliver a thing, it runs like you say. I'm here for this really cool, powerful new smart contract language and all that. Yeah. And then Babylon will give us, hey, you can now build whatever you can dream, you can put it on Babylon. Right. And of course, Xi'an is bringing in that linear scalability to say, now we can say we have this massively sharded space, or we can have more than one validator set. And this also has a bunch of knock-on effects for things like, how does an explorer work? If no single machine can hold the entire network state, how can I go look something up? And there's good chewy problems to be solved there. And at this point, we kind of do
we think long enough to say, okay, we see a path. We are not painted into a corner.
Right.
We now we'll park that in the for Xi'an column with some notes.
Right.
But right now we're all about delivering Babylon.
Right. The important thing is we need to make sure that when people start building stuff on Babylon and they start launching businesses and so forth, that there is the path to give them scalability. Scalability doesn't matter until you have all those people actually doing stuff.
Right.
And then from a technology development point of view, what that means is we need to understand enough about that system so that we can make good decisions now to set that up.
Right.
So things like the Radix engine and how Scripto works and how accounts and transactions work. One of the first questions we always have as we go through the design of these things is, yeah, but is that going to shard?
Right.
Is that going to shard ultimately?
Right.
And making sure that, even if we are not sharded right now, the data structures and everything we're doing is shardable, such that we're not going to have to at Xi'an come back and go, all right, now we got to recreate how Radix engine. Yeah, now we're in trouble. It's like we don't paint ourselves in the same corner that Ethereum is in.
Yeah, well, I was going to ask that question, right? Like, Ethereum went from proof of work to proof of stake. And it took them all of 7 years to do it when they thought it was going to take them 6 months. Right?
And then it wasn't even a fundamental change to how consensus worked. It was just the Sybil mechanism.
Right. And now this idea of dank sharding or proto-dank sharding, all of their so, as someone who's in the crypto space who's going to be skeptical, don't try and snow me. Like, why are we so sure that Xi'an is coming and then it's going to work with our current system if we're only running on one shard?
Mm-hmm. Yeah, I mean, for me, it comes down to the fact that if you're designing a complex system, it's not just finding a better solution isn't just a matter of being more smart and clever about the solution, because there are lots of smart and clever people in the space. It also comes down to the assumptions that you bring into the problem from the beginning. Like which problem you're actually trying to solve.
Right.
And basically other platforms have made a different set of assumptions than we did, because it was a little bit more of a focus on making the next incremental improvement. It's like, okay, Ethereum proved this. Wow, Ethereum is amazing. Programmable distributed ledger.
Right.
Assets started flowing in, applications started launching at it, cool. All right, this thing's kind of slow. How do we make it a bit faster?
Right.
Okay, well, let's try to force some more, you look at that problem, and Emin at Avalanche has a great talk about this, how he's looking at this and saying, he saw this divergence of approaches. It's like, either we need to commit to parallelization and sharding, or we need to focus on maximizing the single pipeline.
Right.
And kind of looked at it and go, well, that sharding is a really difficult problem. I'm not sure if there's a solution there or not, but this way there's definitely something better we can do.
Right.
And so they really maximize that. And Avalanche is a great algorithm for that approach.
Right.
But
maximizing single
pipeline, right.
Exactly.
Whereas we looked at that divergence and said, yeah, this is the harder approach, but it's the way, this one is, you're always going to bump your head against the ceiling if you go this way. You're never going to reach actual linear scalability. Therefore, we must go this other way, even if it's difficult, even if it's risky.
Which we see already, like Avalanche is a good example, Polkadot, Cosmos. It's just, well, let's do another chain, let's do another subnet, let's do another, parachain or whatever it is. But then you get the problem we're talking about before, which is coordination between. Now you've broken that implicit ability to coordinate, and every single one of those chains has the upper limit of their throughput, which kind of is just like juggling that problem.
Right, and the assumptions cascade through the system. So you also look at this and you go, well, if we go this route, man, we're going to have to change the virtual machine. Everyone's looking at Ethereum going, no one wants to change the virtual machine because look at all these smart contracts that are currently on Ethereum.
Right.
And so it's like, well, let's just solve this one part of the problem. So it's like we committed to a problem where we said, you know what, we're going to have to accept the fact that you're not going to be able to just move your Solidity smart contracts over here. We're not going to be able to do take some of these easy, you're not going to be able to just use MetaMask over here. Things are going to be different here, but there's no other way of solving the problem otherwise. So my feeling is I think there are a lot of smart people in the space that might have come to Cerberus if they had gone down that route and committed to it over the course of many, many years to solve that difficult problem.
Right.
But we just decided to do that, and we had the fortunate advantage of Dan starting on this with that approach, going back to the early days of Ethereum.
Yeah, Dan's approach was always, you have to start with sharded first. You have to start with, there is no other way of scaling.
Right.
But then, as you say, it's a really interesting, it's that there were so many things that we had to choose to do differently that meant that it took a lot longer for us to come to market, because as you say, like it's really difficult to like unless you're deep in this space to fully appreciate that you can't just take the EVM. Like if you want if you want to shard state and have a state sharding model at the execution layer, the differences that you have to do even when you build your execution environment, and then how you manage state across shards, and then how you do consensus across shards, and then how you tell consensus how things are related or not related.
Right.
Like everything.
It feels like the last years have been the sequence of really interesting, deep conversations where you're constantly moving all the way up and down the stack. It's sort of like, what if we did it this way? Oh, well, if we did it that way, that would mean this and this and this, and it bubbles all the way up to even like the wallet level.
Right.
And we kind of go, okay, and then we go back to the other way. Well, we want the wallet to be this way. How does that then transition back down the stack? And you keep moving up and down until you have a system that actually, you're not disrupting all the other layers. All the layers are happy working together, and they're all achieving what they need to achieve together.
Right.
If we tried to fork something, never would have got there. It all had to be everything informed everything else.
And this is why we're never afraid of anyone saying like, oh, someone's just going to steal crypto. Like, good luck. You are going to have to just take your network down, all of the smart contracts on your own, put them in the trash can, and then launch a duplicate Radix network.
Right.
Understand how it works.
Right.
Yeah, I mean, and also like, for example, the account model as well, right? Just copying the account model. It's like, no. You'd have to remove everyone's ability to create a public-private key pair-based addressing system, and move everything to an account-based addressing system.
All of your ERC-20 contracts.
Totally native assets.
Totally native assets. You've then, because again, I think sometimes people take the wrong thing away from Scripto. It's like Scripto is more than an interface, but it kind of is an interface to the Radix engine. It's a logical interface to the Radix engine. If you don't have the native assets, you're not really starting from the right point. And then if you don't have the native assets, being able to do the transaction manifest that then leads into consensus, it all comes together. It's funny, we were talking in the car about this idea of skunkworks. Right? Like there is occasionally the opportunity to bring together a group of very intelligent, very motivated people and give them the sole task of designing something for a set of outcomes without having to pay attention to the technology that came before. Technology is just an input, but you don't go, that's the baseline. You don't start with the chassis that you already have to use or whatever. You get to go, look, this is the outcome we want. And that was sort of the no compromises basis that Radix started with Dan and his research, that has then ended up in this incredible full stack approach that Cerberus sort of is right at the bottom of.
That's right, yeah.
So do you think this is why, we say it sometimes, there are incredibly smart people in the crypto space, and they're working on some amazing things. But do you think this is why we think a lot of them aren't working on the right set of problems?
Yeah, that's exactly what we mean, yeah.
It's certainly a big part of it. Consensus is one of the things that had to be, but it's all through the stack. It's when you're thinking only of, I'm iterating upon something that came before to make this a little bit better. Of course, you can do valuable stuff there. A lot of manufacturing has made amazing strides like this, but you don't go from the torch to the light bulb that way, right? You have to go to the complete. Okay, what should it do? What's that blank sheet of paper thinking, and then everything I need to achieve that. You won't get that by saying, let me take this, let me just, turn this dial to 11 in this particular area because I'm feeling a pain point there.
Right. We often even struggle with explaining Cerberus to people because they we've talked internally to Radix about not referring to it as sharding either, because when we say we've got a shard as consensus mechanism, oh, you mean that it's going to be doing this? No. Actually, the whole way we treat it is different than what you're thinking about. It's like there are all of these assumptions that people bring into problems. It's sort of it's a natural instinct. It's like change as little as you can. Focus on changing the thing that you have to change, but this limits the scope of the problem always.
Yeah, we were discussing maybe instead of calling it sharding, like multi-threaded.
Threading, exactly.
I think we'd make a new word. A new word we can, nobody has a preconceived notion about it. It's the wazi-bobbing is what we do.
Exactly. I mean, fascinating. And thank you so much for taking the time to sort of dive deep into it. Thank you very much, Matt. Thank you very much, Russ. And thank you very much for watching.